I'm going to talk about diffeomorphism groups of disks, and my main goal is to explain the statement of a new theorem that I proved with Alexander Cooper's, but I think, as is befitting for this occasion, I'm going to spend quite a lot of time explaining the background to this question, and even maybe background to the background of the question. And let me start a little bit by motivating why should one study diffeomorphism groups at all. So if you're interested in smooth manifolds, as I think everybody in this center is bound to be, then you sort of have to be interested in their symmetries as well. Because any object, any natural object you can think about associated to a manifold, such as perhaps vector fields on the manifold or Riemannian metrics on it or operators on it or anything like that, by virtue of being natural, they have an action of the diffeomorphism group. And you can use anything you know about the topology of the diffeomorphism group to probe spaces like that. So I've mainly, from this point of view, I've mainly thought about spaces of Riemannian metrics, and let me tell you a few results from that direction. The first one is due to Hitchin, before I was born. And it says, if you start with a Riemannian spin manifold of positive scalar curvature, then if the dimension of the manifold is 0 or 1 mod 8, then that space of positive scalar curvature metrics, that's what I mean by this notation here, so Riemannian metrics of positive scalar curvature, is disconnected. So it can and in fact has to have more than one path component. So that means you can find on, for example, a sphere of dimension 0 or 1 mod 8, there's an obvious positive scalar curvature metric that you know, which is the round sphere, but there's another one that is also positively curved, but you can't connect it to the round metric staying in positively curved metrics. And similarly, if the dimension is 0 or 7 mod 8, then he showed that pi1 of the space of positive scalar curvature metrics is non-trivial. So there's a path of scalar curvature metrics. They have positive scalar curvature at all times, but you can't contract it down via a family that has positive curvature at all times. And a few years ago, Boris Bolvinik, Johannes Ebert, and I came up with something. This is a consequence of what we did, which is the sort of natural generalization of Hitchin's result, which is that in the same situation, positive scalar curvature dimension at least 6, then the kth homotopy group is non-zero whenever k plus the dimension of m is 0, 1, 3, or 7 mod 8. And you can see that taking k as 0 and k as 1 recovers Hitchin's two results. But this applies, you'll notice that this says that if you know one homotopy group is non-trivial for this reason, then you know it in 8 degrees higher as well. So for example, it says that the space of positively curved metrics on the sphere, say on the 6th sphere, is the smaller case where it applies, has infinitely many non-trivial homotopy groups. And to mention something very recent, about a month or so ago, Manuel Kranich, Sander Coopers and I, we showed something which looks at similar flavor, but is in fact somehow very different, which is that the same sort of phenomenon with the space of positive sectional curvature metrics. At the level of theorems as I'm stating them here, you can't really tell the difference, but positive scalar curvature, it turns out, has very topologically flavored properties. And it's maybe in retrospect not so surprising that you can prove things about it using topological means. Whereas sectional curvature is much less flexible. So I think this kind of result is more surprising. Although, of course, we don't really know anything about metrics, and we just use topological means to prove this as well. So that's the motivation for sort of spaces of Riemannian metrics. More generally, the diffeomorphism group of any manifold is the structure group for smooth fiber bundles, whose fiber is that manifold. Or in other words, the classifying space of the diffeomorphism group classifies smooth fiber bundles. And that means that by universality, the cohomology of the classifying space of that group are exactly characteristic classes of smooth fiber bundles whose fiber is M. And I think it's basically part of the business of algebraic topology to calculate as much as possible about all kinds of classifying spaces. That's part of the service that we owe to the rest of mathematics, is to provide invariants for things. And so it's somehow something that one ought to understand. But it's very rarely possible to get a complete answer. In fact, there's no manifold of dimension bigger than 3 for which we have a complete answer for the cohomology of this diffeomorphism group. There's no manifold. And sometimes, even when you can get an answer, sometimes it's very surprising. So here's a game we can play. So here's a theorem of Furusawa, Tezuka, and Yagita, from the 80s. So if you look at the torus, the two-dimensional torus, S1 times S1, we look at its group of orientation-preserving diffeomorphisms, and we take the cohomology of that group. Then they proved it vanishes if the dimension is not 1 mod 4. And in dimensions 1 mod 4, they calculated what it is. So in dimension 4n plus 1, it's some function of n. And maybe you can spend a second thinking about what kind of function of n it might be. And I pretty much guarantee you won't have come up with the right one. The correct function of n is 1 plus 2 times the dimension of the space of cusp forms of weight 2n plus 2. Not what you might first guess when you start thinking about smooth manifolds. It's approximately n over 3. In fact, when you get into this business, it's not so surprising that this sort of thing shows up. It turns out there's a close connection to cohomology of arithmetic groups and therefore to automorphic forms and so on. But it's pretty surprising when you first see it, I think. So that's some background. What I mainly want to talk about is diffeomorphism groups of the disk. And I want to start by talking about two tricks to do with scaling. And in fact, they're not so different from some tricks that were mentioned by Professor Colding this morning. Or not this morning, earlier today. It was my morning. So let's start with the following. Suppose we have a diffeomorphism of Euclidean space, f, and I want to write down the following function. So f of tx minus 1 minus t squared times f of 0 all over t. And I want to vary t between 0 and 1. So when t is 1, you immediately see that this is just the original function, f of x. But as t goes to 0, if you let me rewrite my function g of t like this, you immediately see that the second term converges to 0 and the first term converges to the derivative of f at 0. And you believe me when I tell you that this is continuous in t, and so what we've done is we've produced a deformation retraction of the space of all diffeomorphisms to the space of linear maps from Rd to Rd. There's an explicit formula that does that. So it's a deformation retraction from the diffeomorphism group of Euclidean space to the general linear group of linear diffeomorphisms. And then, as you will remember from being an undergraduate, the Gram-Schmidt process deforms the general linear group into the orthogonal group, just by orthonormalizing a basis. So in total, what you discover is that what sounds incredibly complicated, which is the group of diffeomorphisms of Euclidean space, of course, as a discrete group, it is incredibly complicated, but as a topological group, it's homotopy equivalent to just the orthogonal group of rank D. And that's a well-known space in algebraic topology, and we can expect to calculate anything we reasonably want about it. So that's one scaling trick. And this comes fundamentally from scaling outwards. I sort of zoomed in my diffeomorphism to linearize it, because diffeomorphisms are they're smooth, and so by definition, they locally look somewhat linear, and in the limit, they look actually linear. But there's another scaling trick, which is, suppose now I have a homeomorphism of a closed disk, instead of an open Euclidean space of a closed disk, and the homeomorphism is the identity on the boundary. Then there's the following trick called the Alexander trick, which is a similar kind of formula. I want to do the following thing. I want to rescale this homeomorphism by a factor of t, put it inside the disk, rescaled, and then fill in the remaining region with the identity map. At the level of formulas, it's given by what I've written down here. Gt of x is x if the radius of x is beyond t, and otherwise it's a rescaled version of f of t. And when t is 1, this is clearly f. But when t is 0, or in the limit as t goes to 0, we just get the identity map. Right? At any point that's not at the very, very center, that's completely obvious, because the support of this homeomorphism is getting smaller and smaller and will eventually miss that point. And you can check that because I put this prefactor of t, it also converges to 0 at 0. Now this is a bit dubious if you're thinking about the original map as being smooth. Of course, all of these functions are smooth for all t, but the convergence is not smooth. The convergence is only C0. So it's only pointwise convergence. So this is really something about homeomorphisms, not about diffeomorphisms. Even if you start with a diffeomorphism, it turns out it is a diffeomorphism for all time, and the limit is a diffeomorphism, but that's not the correct sort of convergence when we think about groups of diffeomorphisms. There we think about the C infinity topology. So we want to control sizes of derivatives, not just sizes of values. And what this argument shows is that the group of homeomorphisms of the disk, preserving the boundary, so being the identity on the boundary, is contractible. So these are two scaling tricks, one for non-compact spaces that says that the smooth situation is quite simple, you can linearize, and one for compact spaces with control of the boundary, which says that the topological situation is quite simple, you can crunch somehow. And I want to mention how this is related to what's called smoothing theory. So smoothing theory starts with the following situation. You have a topological manifold, and if it has boundary, maybe you assume that its boundary is smooth, and you study the space of smooth structures on that manifold that agree with the given one on or near the boundary. And you have to interpret space of a little bit liberally here, so you can't really make a space naively, but there's many ways to make the homotopy type of the space of smooth manifold. What you can do is, given a smooth structure on M, you can record how it looks near each point of M. And that defines a function that to each smooth structure on M, it gives you a section of the bundle of local smooth structures, so of smooth structures on the tangent space at that point. So essentially, it's just given by exponentiating the smooth structure from a neighborhood of each little point little m to the tangent space of little m. And the fundamental theorem of smoothing theory is that in any dimension apart from 4, where it's not true, this map is a homotopy equivalent. So that means if you want to understand smoothings of a manifold, really the fundamental problem is to understand smoothings of Euclidean space. And then it's the space of sections whose fibers are that, and that's the sort of thing that one can deal with in algebraic topology quite reasonably. Let me say what one can say a priori. I could have done this before the smoothing theorem about the space of smooth structures. Well, the space of homeomorphisms acts on the space of smooth structures. The orbits for that action are essentially, by definition, the diffeomorphism types of smooth structure on M, right? Because each element of SMM is a smooth structure, and if there's a homeomorphism that takes one to the other, that means that they're the same smooth structure. This decomposes as the disjoint union over smooth structure, over diffeomorphism types of smooth structure on M, of the quotient of homeomorphisms by the stabilizer of a smooth structure, which is the diffeomorphism group of M. Okay. As I said, this isn't quite true. You can't really make a space of smooth structures. You shouldn't really take a quotient in any sort of naive sense like this either. But at a moral level, this is true, and with the correct technicalities, it can be made true. And similarly, if you do this to Euclidean space, well, there's only one smooth structure on Euclidean space in dimensions other than 4. So you just get homeomorphisms of RD modulo diffeomorphisms of RD. That's what you get for, so that describes the fibers of the bundle whose sections one is taking here. Now, so let me just write top D for homeomorphisms of RD. This will show up quite a lot. So in other words, what I just said at the last line was that the space of smoothings of RD is the homogeneous space top D mod OD. So let's apply this to the disk. If we apply it to the disk, it says that homeomorphisms modulo diffeomorphisms is equivalent to a path component of the space of sections of some bundle over a disk. But the disk is contractible, so whatever that bundle is, it has to be a trivial bundle. So sections just means maps from the disk to homeomorphisms of RD modulo diffeomorphisms of RD, which we can write as top D mod OD. And because everything was relative boundary, it's maps from a disk that are fixed on the boundary. But on the other hand, I just said a few slides ago that homeomorphisms of the disk is contractible by this Alexander trick. So if I take homeomorphisms modulo diffeomorphisms, that's a contractible space modulo diffeomorphisms. And that's the definition of the classifying space of a group. You take any contractible space modulo that group. So the left-hand side is the classifying space of the diffeomorphism group of the disk, and the right-hand side is just the default loop space of homeomorphisms modulo diffeomorphisms of Euclidean space, with a little decoration because it's only one component of that space. And if you like, you can loop this one more time, and you can say the group of diffeomorphisms of the disk is the D+1 fold loop space of top D mod OD. And as I tried to claim, the orthogonal group, I mean, it's a finite dimensional cell complex. It's a Lie group. We know very much about it. So you can consider it to be completely understood, but that means understanding diffeomorphisms of the disk is essentially equivalent to understanding homeomorphisms of Euclidean space, in the sense that they're related by this formula where the other term is known. But the advantage of diffeomorphisms of the disk is that you can use that you know they're diffeomorphisms, i.e. they're smooth, and that gives you many more tools to work with. For homeomorphisms of Euclidean space, it's very difficult to know where to get started. There's no local structure you can use, but for diffeomorphisms you can. So let me tell you a little bit about what we know about diffeomorphism groups of the disk, and that's completely equivalent to knowing about homeomorphism groups of Euclidean space. So the classical approach that Marcus mentioned in his talk to studying diffeomorphism groups breaks up as sort of 3 steps. First is that you look at a much weaker notion of equivalence, which is just homotopy self-equivalences of that manifold, maybe a well boundary if there is some. And that's just, you're in the realm of pure homotopy theory and you have to calculate what you can about it. The second step is to promote homotopy equivalences to what are so-called block diffeomorphisms. I won't try to say precisely what block diffeomorphisms are. One way to think about it perhaps is, which is not rigorous and is not true, but is a way to think about it, is as a coarsening of the topology on the group of diffeomorphisms. So on the group of diffeomorphisms, a continuous path in the group of diffeomorphisms is an isotopy. In this block diffeomorphisms, a continuous path is a so-called pseudo-isotopy, which means it's a diffeomorphism of m cross interval, but it doesn't have to be fibered over the interval like an isotopy does. It's just a diffeomorphism that can mix up different times in the interval direction. In a sense, it's a more complicated object, but it can be analyzed by surgery theory, and so it's the object. It's essentially what you can analyze by surgery theory, are block diffeomorphisms. But then you have to deal with the fact that block diffeomorphisms are not what you were interested in. What you were interested in was diffeomorphisms, and so you have to understand the difference between these. And that's the subject of pseudo-isotopy theory, and that's where algebraic K-theory enters the story. But here there's an issue. The first 2 steps, even though you may have difficulties in pursuing them, at least in principle, you can hope for a complete answer. In the pseudo-isotopy step, it's well known that the description of pseudo-isotopy is only valid in a certain range of degrees, known as the pseudo-isotopy stable range. And a very deep theorem of Egressor is that this range is at least, we don't really know what it is, but it's at least this function here, which is approximately the dimension of the manifold divided by 3. And I showed a couple of years ago that whatever this pseudo-isotopy stable range is, it's at most d minus 2. So it's somewhere between d over 3 and d minus 2. Most people probably think it's d over 2. But even if you knew perfectly about that, outside of this range, the methods, the classical methods of algebraic K-theory and so on, wouldn't even propose an answer. So in the case of a disk, this exact program that I've outlined here was followed by Farrell and Xiang, and they got the following answer. If you look at diffeomorphisms of a disk, rationalized, rationalizing helps with every step involved. Then if the disk is even, you get nothing. And if the disk is odd dimensional, you get 1 class every 4 degrees. This is essentially the algebraic K-theory of the integers, with degrees shifted down by 1. But this is only true in this pseudo-isotopy stable range. So as far as we know, that's approximately d over 3. The next result I'd like to mention is due to Watanabe. He first studies, in particular, odd-dimensional disks. So for any dimension at least 5, and there's a parameter at least 2, he proves that the homotopy groups of the diff of this 2n plus 1 dimensional disk, 2n plus 1 at least 5, surjects onto a certain vector space called AR. And let me tell you what that looks like. AR is the following thing. It's the vector space spanned by trivalent graphs, which is what I've tried to draw here, whose Euler characteristic is minus R. So that means they have, what, R minus 1 plus 1, R minus 1 loops. Modulo the following thing. Whenever you see an eye shape in your trivalent graph, so whenever you see a local picture that looks like this eye, you're allowed to replace it by the difference of these two local pictures that look like an H and an X. This is the so-called IHX relation. It's a form of encoding the Jacobi relation for Lie algebras. And also modulo certain signs, which is not worth any of our times me trying to explain to you. They're very complicated. But you take this vector space, so it's spanned by trivalent graphs of a known number, of a known first Betti number, modulo these local moves. And he proves that whatever this homotopy group is, it subjects onto this space of graphs. And it's very difficult to compute the dimensions of these spaces of graphs. The first few are known. They go 1, 1, 1, 2, 2, 3, 4, 5, 6, 8, 9. But this ... I mean, at some point we definitely don't know the answer anymore, and it's not much further than this. But some general properties are known. So, for example, it's known that the dimensions carry on getting big. And most recently, in this direction, Watanabe proved an analogous theorem. In this case, incredibly, he proved it for the 4-dimensional disk. And he proved a very similar statement that the homotopy group pi r of this subjects onto something I've called AR even. If I tried to write out what it was, I would write exactly what I wrote here, because the difference between the even and odd decorations are exactly to do with what these signs are, which I didn't tell you anyway. So it's of a similar flavor. It's trivalent graphs modulo IHX with certain signs, but the signs obey slightly different rules. In particular, it's a different vector space. They have different dimensions, but the first few are also known, and they're not all 0. So using this, when R is 2, he showed that pi 2 of the classifying space of the diffeomorphism group with the 4 disk is not trivial, which resolves a tremendous number of questions in 4-dimensional topology. This was known as the Smale conjecture. It's, of course, well known that in high dimensions, the diffeomorphism group of a disk is not contractible. And in very low dimensions, 2 and 3, it is contractible by theorems of Smale and by Hatcher. And for 4, it was open. And he proved, he proved this, which is incredible somehow. He only proved it for the 4 disk, but one expects a very similar story if you replace 4 by 2n, analogous to this story here, which holds for all big enough odd numbers. Sorry. And the third theorem I'd like to mention is due to Michael Weiss. Closely related to this classical story that I mentioned about smoothing theory and so on, is the fact that in the limit as the dimension goes to infinity, the infinite orthogonal group and the group of and the infinite top group, so the group of homomorphisms of Rd as d goes to infinity, is a rational equivalence, meaning it's an isomorphism on rational homology, homotopy, cohomology groups. But of course, we know the cohomology of the infinite orthogonal group. It's not very difficult. It's a polynomial ring on a sequence of classes known as Pontryagin classes, 1 in every degree divisible by 4. And so that must be the same for the group of homomorphisms of this infinite dimensional space as well. Now, when you think about finite orthogonal groups, let me say with even index, so O2n, the usual definition of these Pontryagin classes, which is in terms of Chern classes of their complexifications, immediately show two things. They show that the nth Pontryagin class, where the n is the same as the n in 2n, is the square of the so-called Euler class, and the n and the ones above n are all 0. That's the easy consequence of just from the definition in terms of Pontryagin classes. Now, if you consider them as defined on BO, you use this isomorphism to think about them as being on B top, and then you pull them back to B top to n. It's not obvious in either direction whether this should or should not be true. And Michael Weiss spent a long time trying to show that it was true, and then changed his mind and decided that he would show it wasn't true, and indeed it's not true. Let me be vague about what exactly the conditions on n and I are here, but he proved that there are classes in the homotopy groups of B top to n which pair non-trivially with these Pontryagin classes in degrees n plus I, for I being at least 0. So in other words, it's exactly saying that these two equations tend not to hold in the group of homomorphisms of Euclidean space. And a consequence of that, because of this smoothing theory story, is that you get various homotopy groups of the group of diffeomorphisms of an even disk in degrees congruent to 2n minus 1 mod 4 and starting at 2n minus 1. So so these is the results that are known basically about homotopy groups of diffeomorphism groups of disks in high dimensions. Based on this, Alexander Coopers and I decided that we would try to calculate outright as much as possible about these homotopy groups, inspired very deeply by the arguments of Michael Weiss. Michael Weiss's argument is somehow, in a sense, qualitative. He doesn't try to determine what the homotopy groups are. He proves they have to be non-zero because he finds certain elements that on the one hand transform one way and on the other hand transform another way, and that's not possible if the group is 0. But he doesn't try to determine what the groups are. And we tried, our idea was to use similar methods to try to just determine outright what the groups are. And the first sort of paper in this story just came out a month or so ago. And here we do the following 3 things. We fully determine what the groups are in degrees up to about 4n. Above that range, we also determine them with certain exceptions, so outside of certain bands, as we call them. And we also understand something about the structure of these bands. And I think the easiest way for me to explain to you what these 3 things mean is to show you a picture, and then it's much more comprehensible. So the picture looks like this. I'll spend quite a lot of time on this. So this is plotting in the horizontal direction the dimension of an even disk, so starting at 6, 8, 10, and so on. And vertically, it's plotting homotopical degree. And we have the following meaning. So when there's nothing, that means the group is 0. Each one of these orange blobs is a copy of the rational numbers and corresponds exactly to one of these classes found by Michael Weiss. And if you see them in each column, you get one every 4 degrees, just like he suggested. And then there's this, this sort of spectral pattern, these bands. And in the bands, that means we don't quite know what's going on. But there's 2 kinds of not knowing what's going on. There's the orange and the blue kind. The orange kind is, there may be other stuff there, but the orange dot is also definitely there. And the blue kind is, there may be other stuff there, and we don't know whether the orange dot should be there or not. Okay, so there's uncertainty, but sometimes the uncertainty can cancel with the orange dots, and sometimes it can't. And you will notice that that can't be the full story, because I've drawn some orange dots in positions that are inside blue bands, and that doesn't quite fit with what I said. That's true. There's another mechanism at play, which is that in this business of detecting non-triviality of Pontryagin classes, if you pull something back from B top to B top 2n and it's non-zero, then it's also non-zero on all the intermediate groups, of course, on top 2n plus 2, 2n plus 4, 2n plus 6. What that translates to in this picture is that whenever there's an orange dot, you can fill in the line of slope -1 under it until you reach this point here. So these orange dots are there because above them somewhere, there is an orange dot in an unobstructed region, like here. So this generates this whole line. But down here, for example, this orange region here, we don't quite know, and so we can't deduce anything about the region in between. So this is the general pattern. There's an underlying pattern of these Weiss classes, 1 every 4 degrees, that correspond to Pontryagin classes. And then there's some uncertainty overlaid onto that, but the uncertainty comes in this sort of pattern. There's lines of various slopes, and there's bands of various widths around each such line, inside which we don't quite know what's going on. It's a bit difficult to see in this picture, but as you increase as you go from one of these bands to the next one, the slope goes up and the width goes up as well. And the consequence of that is that in each column, if you go high enough, everything is going to be obstructed and you don't know anything anymore. So for each fixed disk, we only get finitely much information. But for each fixed degree, we get infinitely much information. So this is me just trying to write it out in mathematics again. So in dimensions starting at least 6, if the homotopical degree is less than 2n-1, then this group vanishes. Oh, sorry, one more thing I should have said on this picture. One more feature that I didn't explain is this dotted line down here. This is the Egressor stable range. So this is what, as far as we know, is the pseudo-isotopy stable range, is this region down here. It's about dimension of the disk divided by 3. So we're getting information up to about twice the dimension of the disk. So we're improving by a sort of factor of 6 on what was known before. But going back to this, the pattern is that below 2n-1, there's nothing. Above 2n-1, there is some uncertainty generally. But if the dimension is not in the union of these bands, then it's either Q or 0, depending on whether D is 2n-114 or not. That's just the mathematical formulation of the chart. And there's a way of reformulating it, which is a little bit stronger, but a little further away from talking about diffeomorphism groups, which is that we can think about the fibration sequence that relates O to N, top to N, and top. So those are 3 groups, each contained in the next one. And so there's 3 homogeneous faces you can make, and they fit into a fibration sequence, as any sequence of groups does. And the reason for doing this is that top, I told you, we know everything about, because it's rationally the same as O. And O to N we know everything about. So the middle term is completely known, and indeed its homotopy has 1 class every 4 degrees, starting in 2n-1. So this exactly contributes to all the Weiss classes. And then we can encode in this other term all these bands, this unknown region. So the reformulation is that in dimensions at least 6, the homotopy groups of top mod top to n are supported inside these unions of degrees. These are exactly the bands with a little offset maybe. But it's this sort of explains a little bit why the bands versus the dots are decoupled, is that they come from these 2 different spaces. But of course they might interact a little bit because this map might be non-trivial. That's why we can't rule out the possibility that all the dots are there. And there's one more bit of structure that I didn't mention on the chart, which was that the bands had alternating colors, orange and blue. That comes from the fact that I'm talking about diffeomorphisms of a disk fixing the boundary, but that has an outer automorphism by conjugating by a reflection of the disk. So the reflection of the disk doesn't fix the boundary, but if I conjugate by something that does fix the boundary by it, the result fixes the boundary as well. So all of these spaces, in fact, have involutions on them. And these 2 colors correspond to the eigenspaces of that involution. So we show that on these Pontryagin Weiss classes, the involution acts as -1 always. And on the bands, it acts as -1 to the R in the rth band. So some of them, it acts in the same way as the Pontryagin classes, and in that case, there could be cancellation, and we don't know. Those correspond to the blue bands. And in some cases, it acts in the opposite way to the Pontryagin classes, and then this map must necessarily be 0, because it's mapping between eigenspaces with different eigenvalues. And so there can't be any cancellation. So yeah, that corresponds to the orange and blue bands on this chart. It's the eigenspaces of the involution. And we also determine, to some extent, what happens in the first band. Let me briefly go back to the chart. In fact, there's a secret first band, which I didn't draw, which is parallel to this lower edge. And I didn't draw it because we completely calculate what happens in that range, and we showed that there's in fact no uncertainty. So in fact, strictly speaking, that's the first band, and this one here is the second band. But this is the one I'm talking about. It's the first band where we don't know what's going on. And we calculate that in this range of degrees, 4n minus 9 to 4n minus 4, so that's exactly the width of that band, the homotopy groups are calculated by a chain complex of this shape. So q squared, q to the 4, q to the 10, q to the 21, q to the 15, and q cubed. And a little more information that here the differential injects. But unfortunately, the method we use for this, we can calculate the dimensions of these groups, but we can't determine, we've really computed dimensions of groups, not a basis. And we can't determine what the differential is, because really each of these is an isomorphism class, a vector space, not a vector space. But if you do some arithmetic, you see that the Euler characteristic of this complex is 1. So whatever the differentials are, there has to be some homology there. And whatever the homology is, this band is in the +1 eigenspace, and so it doesn't interact with the Pontryagin classes, and so whatever it is, it injects into the homotopy of the diffeomorphism group. So it has to be at least one-dimensional by Euler characteristic. It could, of course, be bigger. By analogy with Watanabe's theorem for the 4-disk, if you go through his argument at a sort of very coarse level and work out how the degrees should behave if you scale 4 to be 2n, you discover that this first class he finds should be in degree 4n minus 6. So his argument should show, if it went through in high dimensions, which I'm not sure if it does, and he hasn't been willing to commit to saying it does. But if it does, it would say that in dimension 4n minus 6, there's at least one non-trivial homotopy group. And 4n minus 6 exactly corresponds to this position, the q to the 21. And that is indeed consistent with the homology of this chain complex being exactly one-dimensional, being q in this degree. That could happen. You can invent differentials that make that happen. And my guess is that that is what does happen. But with the technology that we're using, we can't really control these differentials, and so we can't really proceed past this point. I'll tell you a few things about what goes into proving such a thing. So from the philosophical point of view, I've already mentioned when I was talking about the classical approach to computing things about diffeomorphism groups, and when I was talking about smoothing theory, that most of the results in this flavor of geometric topology are somehow relative. They don't directly tell you about diffeomorphisms. They tell you about the difference between homeomorphisms and diffeomorphisms. That was smoothing theory. Or they tell you the difference between homotopy equivalences and block diffeomorphisms by surgery theory. Or they try to tell you the difference between block diffeomorphisms and diffeomorphisms by pseudo-isotopy theory. And so if you want to get some absolute information, you have to compute one absolute thing, which in the classical strategy is you compute homotopy equivalences first, and then you put together, you combine that with these relative terms to obtain an absolute calculation about, say, diffeomorphisms. That's somehow endemic in this subject, that the good descriptions tend to be of relative objects. And when you want to put them together to get something about an absolute object, you have to go to some trouble understanding how they fit together. So Weiss thought up, during his argument about these Pontryagin classes, a new kind of relativization, which is as follows. So if you start with a manifold with boundary, whose boundary is a sphere, and let's say half the boundary is a name for the lower hemisphere inside the sphere. And what he shows is that if you think about diffeomorphisms of the disk as being a subgroup of diffeomorphisms of the boundary by embedding a disk next to the boundary of the manifold, then the homogeneous space for that homomorphism of groups is equivalent to the space of self-embeddings of the manifold, not preserving the entire boundary, but only preserving half the boundary and flexible to move on the other half of the boundary. So the power of this is that under moderate conditions on M, embedding spaces can be analyzed using a tool known as embedding calculus. they can be analyzed in principle completely. It's like surgery theory or smoothing theory, that in principle it gives you a complete answer. There's no question, like in pseudo-isotopy theory, about whether or not it works. This embedding calculus always works. Of course, you can have difficulties in getting it to do what you want, but in principle it gives you a complete a method to understand everything you want about this embedding space. And that suggests, of course, the following strategy: find some manifold for which you can calculate things about this embedding space, and you know, maybe for other reasons, something about its group of diffeomorphisms, and then run this game backwards to deduce something about the diffeomorphism group of the disk. So this is the strategy that we pursue, and at this level of detail, it's completely analogous to the strategy that Michael Weiss pursued in his theorem, and indeed our idea comes from his. But the way we go about doing it is somewhat different. So let me first tell you what the wise choice of manifold M to take is. The wise choice of manifold to take is the higher dimensional analog of a genus G surface with one boundary. So in other words, it's the disk connects some with G copies of Sn times Sn. So in dimension 2, that looks like my picture. And the reason this is a good choice is that we know in high dimensions, in fact in many dimensions, we know these days a tremendous amount of things about the diffeomorphism group of these manifolds, especially in the limit as G goes to infinity. So the first theorem that got this started is the theorem of Madsen and Weiss, which is exactly about this situation in the dimension I drew it, so in dimension 2. And then more recently, Songalatius and I worked out how to adapt those ideas to work in high dimensions. So they work at the end of the day, we have the result in all even dimensions. And it says that if you take the cohomology of the diffeomorphism group of this manifold, say with rational coefficients, there's a fancier version integrally, but it's more difficult to say what the answer is. And you take the limit as the genus, so the number of summands goes to infinity, then the answer is incredibly simple. You get a polynomial ring on certain symbols, and those symbols are indexed by monomials in the Euler class and certain Pontryagin classes. There's another tool in this sort of subject, which is to do with how does each term in this limit compare with the limit? So how do you compare the genus G answer with the genus infinity answer? It turns out for the story that I'm trying to explain, we only need somehow the limiting case. We don't need to worry about this stability phenomenon, although that's very interesting in its own right and important for other applications. In analogy with this result, a very recent theorem of Alexander Berglund and Madsen is that we know a comparable amount of information for these block diffeomorphism groups and for the groups or monoids of homotopy automorphisms of these manifolds. So I've tried to write it in a way that's as parallel as possible, and maybe it looks incredibly similar to you. So it's again a polynomial ring or a free-graded commutative ring on some symbols indexed by some set. I won't try to tell you what they are, but these indexing sets here are much more complicated than the indexing set here of monomials in these symbols. It's indexed by homology classes in something like a group cohomology of outer automorphism groups of free groups. And their theorem is phrasing it in those terms, but we don't know how to compute those vector spaces. So we can't enumerate these bases B prime and B double prime in the way that we can with this basis B. And in some sense, probably we will never be able to enumerate them. I mean, it's a little bit like just trying to find a formula for the ith prime. I mean, maybe you're not supposed to. It's a little bit like homotopy groups of spheres, maybe. The correct question perhaps is not, can we write down what all these groups are? But at the formal level, the theorems are incredibly similar. And maybe one observation which is interesting, especially if you think about the classical perspective where you try to compute things about diffeomorphism groups by going through homotopy automorphisms to block diffeomorphisms to diffeomorphisms, is that the answer for diffeomorphisms is a lot simpler than the answer for what you start with or the intermediate steps, which is quite interesting and probably means that it turns out in the pseudo-isotopy stable range, this complication doesn't really show up. So in that range, you don't really see the difference. But it sort of does suggest that maybe this classical pattern of starting with homotopy equivalences and trying to progress to diffeomorphisms is maybe in some sense a little wrong-headed, because you may be answering more difficult questions to start with than you really needed to. So this is the manifold we choose, this high-dimensional version of the genus G surface. And then we have to calculate very many things. And there's two kinds of difficulties involved. So this, as I mentioned, this embedding calculus machine tries to calculate homotopy groups of spaces of embeddings. And it's a machine in the sense of algebraic topology, which means you're allowed to try, basically. It's not an algorithm. It just means there's a framework that you can try to use, and it has many, many steps. And at every step, you may not know how to proceed, and there's no guarantee that it's possible to work out how to proceed at any step. So it's sort of miraculous, the subject of algebraic topology, especially its calculational side, because there's no reason you ought to be able to calculate almost anything from the definition. But nonetheless, most of the time, people somehow, by some sort of ingenuity, can. And that's what happens here. So what it comes down to for us is we need to compute two things. We need to compute the cohomology of Cartesian products of these manifolds WG1 relative to a certain subspace. It's the diagonal plus a little bit of the boundary. And we have to compute homotopy groups, rationalized, of the space of configurations of k points in this manifold WG1. And configurations means ordered configurations. And in both cases, there's an action of the symmetric group, here by reordering the configurations and here by reordering the factors. And there's an action of the diffeomorphism group of this manifold, just by naturality, or by functoriality of both sides. And what we need to do to proceed with this embedding calculus business is to calculate what these groups are as representations of the symmetric group and of the mapping class group of this manifold. And depending what you want to achieve, maybe you just want to estimate what those groups are, like say in what possible degrees they can have homotopy or cohomology groups, or maybe you want like a literal formula for what the characters of these representations are. The first of these can be done, it took us a long time to realize this, but it can be done very quickly using a recent theorem of Dan Peterson, which basically just gives you the answer straight away. The second is much more complicated. I was going to explain how it goes, but I think I won't. It's not very difficult, it turns out, to get a presentation for the homotopy groups of these configuration spaces in all degrees considered as a Lie algebra under the whitehead bracket. We can just write down a presentation, so generators and relations. But giving a presentation for an algebraic object is not very useful for knowing things like, is it 0 or not? And what we really want to know is, like, what is the character in degree 10? And so you have to do quite a lot of work to go from having that presentation to having a formula for the character, involving lots of causal duality and algebraic manipulations. But it's possible, and we get complete answers for those. And this lets us completely determine what are so-called the layers of the embedding tower. So the embedding calculus is an approximative system, and the things that you can generally calculate are the differences between the two adjacent approximations. So like the kth versus the k minus first. And we can completely determine these layers, these relative terms, but we can't determine their interaction. That's exactly this question about determining the differential in this chain complex for the first band that I explained a few moments ago. So we're left to just say the embedding calculus is something supported in this range of degrees and nothing outside of that range of degrees. And this range of degrees, you don't have to remember the formula, but it corresponds to these darkly shaded regions of the bands in my chart. I didn't explain on the chart why the bands, they came in two colors, blue and orange, but they also came in two shades, dark orange and light orange. The two shades correspond to the two sources of ambiguity, and the dark orange comes from the ambiguity here, that we can't control the interaction of the layers, but that doesn't matter to get this band pattern. But it would matter if you wanted to know exactly what the answer is. And the second difficulty is that while by these theorems of Madsen Weiss and Kalatius and myself, we have very good understanding of the cohomology of these diffeomorphism groups, the method, as I outlined it, needs to know the homotopy of the diffeomorphism groups. And in general, those are quite different things, but here, the fundamental group of this or in other words, the mapping class group of this manifold is close to being basically either the symplectic group if n is odd, or the orthogonal group of a form of signature GG if n is even. So it's a big arithmetic group. It's massively complicated. It's nowhere near being a nilpotent group. You cannot in any way expect to compute homotopy groups out of cohomology groups by any formal procedure for a space like this that's completely not nilpotent. It's impossible. So somehow you have to deal with that. And you can deal with it by getting rid of this arithmetic part of the fundamental group. So you can make what's called the Torelli group, which is diffeomorphisms of the surface that act trivially on the middle homology of the, sorry, I said surface, diffeomorphisms of the manifold that act trivially on the middle cohomology of the manifold. That has the effect of eliminating this big arithmetic group from the mapping class group, but of course it's a very different group. And in two companion papers earlier, we proved two things about this Torelli space, or the classifying space of the Torelli group. We proved that it is nilpotent, so there is a good connection between its rational homotopy and rational cohomology groups. And we completely computed the rational cohomology groups in high dimensions, so in dimensions at least 6. So doing that, you can try to calculate the homotopy groups by an algebraic procedure, so-called unstable atom spectral sequence. And you don't succeed, you get again some ambiguity. But the main term you get is one class every 4 degrees, starting at 2n-1. These are exactly the orange dots on the chart. And this ambiguity that you get where we can't quite determine what goes on, that is the other, the lightly shaded region on the chart. But it's also relatively small in terms, it's supported in a narrow range of degrees, whereas these Pointryagin classes are spread out across all degrees, starting at 2n-1. So those are the two difficulties. Let me end with what you might think if you were incredibly optimistic. So a diffeomorphism is, of course, an embedding. And you can apply this machinery of embedding calculus to diffeomorphisms considered to be codimension 0 embeddings. The machinery exists always, but to converge, you need a condition on the codimension of the embeddings. And that condition is certainly not satisfied for diffeomorphisms. And in fact, not only is the condition not satisfied, but one can check here that it definitely doesn't converge. Frest, Turchin, and Willwacher have essentially, up to some subtlety that I won't say anything more about, worked out what embedding calculus predicts for diffeomorphisms. And what it predicts is the following. It starts off with classes in degrees 2n-4, 2n-8, 2n-12, ... And then there's some stuff in degrees around 4n, degrees around 8n, degrees around 10n, and so on. This is a bit misleading here. It's not always one-dimensional, and it's not always in 1 degree, but it's clustered near multiples of 2n. And we can compare this with my theorem with Cooper's, and you see that there's two phenomena. Firstly, this has missed these Michael Weiss classes, these Pointryagin classes. They're not there. But secondly, it started with this business here in degrees 2n-4, which is not supposed to be there. If you think about it, one way to explain having too many classes in degrees 2n-4 and not enough classes in degrees 2n-1-4 is if the difference between these spaces exactly had classes every 4 degrees. And you might be led to ask yourself, could there be rationally a fibration that tells you that diffeomorphisms of the disk is not the same as diffeomorphisms of its embedding calculus approximation, but the difference is something that has homotopy groups Q every 4 degrees. My guess is some version of L theory, which is well known to have homotopy every 4 degrees, a copy of Q, and also to be closely linked to Pointryagin classes. So you might ask if this were true, and I'd like to finish by offering a few bits of evidence for this. As I said, the first bit of evidence is that this is consistent with everything we know. It would explain Watanabe's results, because the theorem of Turchin, Willwacher, and Fraisse calculates homotopy of this approximation, and it has these graph cohomology classes in it. In fact, that's what it mainly consists of. It would also explain Weiss's result, because the classes here that don't cancel against these spurious classes that Fraisse, Turchin, and Willwacher find would come from behind and give Weiss's classes. And it fits with every other calculation that I know in this sort of area. The second piece of evidence is a recent theorem of Ben Knudsen and Alexander Cooper's, which is that somehow that this failure of convergence, the difference between diffeomorphisms and the embedding calculus approximation to diffeomorphisms, is quite robust. They prove that it doesn't really depend on the manifold. As long as the manifold is a little bit connected, maybe too connected and its boundary is a sphere, the boundary of sphere is probably not very important, but the fact that the manifold is a little bit connected is probably important for this. And you might ask yourself, what other things in this sort of area do we know where they sound like they depend on the whole manifold, but it ends up they only depend on the fundamental group of the manifold or something like that? And maybe one thing you think of is exactly L theory, because of the so-called pi-pi theorem, which tells you that L theory of X is actually L theory of the fundamental group of X. So that would somehow be compatible with this. And the third piece of evidence is a recent theorem of my PhD student, Niels Prigge, which he's proved that the family version of the signature theorem does not hold on the finite stages of the embedding calculus tower. So the family signature theorem is a theorem, and so it does hold, generally, for fiber bundles. It's an analog of the statement of the Hirzebruch signature theorem. Hirzebruch signature theorem says that there is two things, one of a very global nature, which is the signature of the intersection form, and the other of a very local nature, which is the integral over the manifold of the first Pontryagin class, maybe divided by 3, or some polynomial in Pontryagin classes in general. The family signature theorem is similar in spirit. It says if you have a fiber bundle with fiber sum manifold, on the one hand, you can associate a local system of intersection forms given by the intersection forms of the fibers, and you can attach a characteristic class to that. And on the other hand, you can attach a certain integral, a fiber integral of a certain polynomial in Pontryagin classes. And the family signature theorem says that for fiber bundles, these agree. So in other words, on B diff, these two things are the same. Now, on this embedding calculus tower, it turns out you can define these two things. In fact, they're both defined very near the bottom of the tower. But this equation between them doesn't hold, ever. In the sense that there's no k for which it holds for all manifolds M. You can't quite go from that to the limiting statement. There could be something dangerous going on in taking that limit, but it certainly suggests to me that the family signature theorem should not hold on B of T infinity. And the failure of that holding would one would expect it to be accounted for by a copy of symmetric L theory, which is the universal home for signature type invariants. So that's the evidence I have for this story. Proving that this could possibly be true is going to have to involve different methods to how Coopers and I have dealt with our theorem. At least one is going to have to do the embedding calculus side in a more modern way. In a sense, what we do is rather classical from that point of view. There are much more modern operatic or higher categorical ways of dealing with embedding calculus. And it may be that doing it that way and using Willwacher style graph complexes, one can actually establish this, this vibration. Okay, thank you very much for your attention.